Alright, hi, welcome to SAS X7. Today is the 7th Serendipity as a Service. This is the Bitmage, founder of Conwell Industries. We're going to talk about approaches towards understanding and formulating problems today. So, whenever you're working on something, whenever you're solving a problem, solving a problem is probably the most fundamental task, generically expressible. Solve a problem. Yeah, that's probably the most abstract way of expressing a task, to put out a fire or something. So, how you sort of start out in solving a problem is probably how you work in general, because this is the most abstract way of describing how you work. To go from a certain state of the problem not being solved to a state of the problem being solved, or some progress upon those states, that should be the primary incentive towards anything that you do when it comes to solving problems. So, the first and foremost thing that comes to mind when trying to solve a problem is formulating them properly. So, understanding the vocab of the problem, the jargon of the problem, the jargons of the problem is very important. It has a very specific name. When you see it from the perspective of computer science, they are called domain-specific languages. If you also happen to have programmed in Lisp a little, DSLs are sort of a big thing out there. Just create your own DSL. So it's sort of a different paradigm of programming in itself. Programming languages. So Racket is pretty heavy on this. It's the newer version of Scheme, newer variant of Scheme. The programming language oriented programming language. So building languages to solve problems is sort of a very powerful viewpoint, and these problems can range from anything. So Lisp, whenever I say Lisp, we should probably just substitute it with symbolic algebra or symbolic computation. So representing any state or any behavior or any process or anything, any transformation by a symbol. So it could be either code or data. So it could be behaviors or attributes that can be represented as symbols, and their transformations in a certain way would sort of help you formulate the problem if those behaviors, attributes, and transformations can be expressed in higher abstractions. So, for example, if I wanted to make a cup of coffee, I need to know the abstraction. Okay, the problem is making up a cup of coffee. So, yeah, you first either have to first clarify the problem. I don't want to make a cup out of actual coffee, as in I'm pouring. Yeah. So natural language is where the failure is at. Making a cup of coffee, humans sort of understand it right away, but then communicating it with someone who's going to solve the problem, let's say not a human, probably a machine, making a cup of coffee is super confusing. I mean, what am I supposed to, am I supposed to freeze coffee in a cup like mold and have a cup of coffee or something? So yeah, that sort of natural language is very confusing. So let's say I want coffee in a cup. Yeah, give me a cup of coffee, a cup with some coffee in it. Yeah, I have to begin being more precise with the problem right away. Again, after that, I also need to highlight my base abstractions on what I'm working on. So I'm not going to grow coffee beans. I'm not going to want it to grow coffee beans right now. I would like it to probably use instant coffee. I am that instant coffee kind of guy. It probably just takes 2 minutes. Yeah, just takes 2 minutes. I microwave my water, pour in some instant coffee, and that's it. So yeah, and I put in some L-theanine. So yeah, that's mostly it. So this recipe of take around I think 6 grams of instant coffee gives me around 150 milligrams of caffeine. I explicitly put in around 200 milligrams of L-theanine. Heat the water up until 2.5 minutes. And I also have to mention how much water. Every day I measure it in a cup. So the cup itself, fill the cup with water, put it in the microwave, heat it up. All of this vocabulary is really necessary to solve the problem, to formulate the problem, expressing what has to be done. You have to constrain the abstractions, the base abstractions. So I have access to a microwave, I do have water with me, my resources. The initial data that I have water, I have instant coffee, I have a cup. Alright, so I have all the base abstractions are necessary when formulating a problem, what you're working on. And to really work well and quickly with something, if you're going to solve a problem, a sort of problem again and again, that's when you are trying to facilitate the application of a domain again and again. So rather than facilitating a specific solution, you're facilitating a specific sort of solution. So a very good example of this, let's say, would be a convex optimizer. So a library that helps you with convex optimizations. The vocabulary needed for this, of course, roots from matrix algebra, calculus. So all those base abstractions are necessary. Now you do not want to be programming with registers and caches and program counters when sort of dealing with a problem of convex optimization. You will probably want to deal with matrices, you will want to deal with constraints, you will want to deal with gradients, you will want to deal with iterations, fixed point iterations, that sort of stuff. To express those in terms of the base abstractions that you have, as in any higher level programming language, you could use either Python, MATLAB, C++, whatever you're using, is the first step towards effectively solving a problem. To build that level of base language, vocabulary, jargons, DSLs. DSLs is the main word that I'm going for, domain specific languages, is very important in actually understanding, formulating, and having a generic class of solutions to express the class of solutions to problems. So the DSL for barista is going to be much more elaborate than what I just used to formulate the problem. He or she knows the different kind of roasts, how their tooling works, the machines, what they're going to do with it, what exactly is the process of what's happening to the coffee exactly. Rather than heating it for 2.5 minutes, they'll probably think of it in terms of temperatures, probably, I don't know. So the more elaborate your language, the more intricate and valuable your solutions. So elaborate in the sense of the amount of base abstractions your DSL is built on, the power of those abstractions, the expressiveness of those abstractions, and the encapsulation of them all into parent abstractions that help you sort of express the problem conveniently, express solutions conveniently for further application down the line. That is the crux of why you should use a DSL, why you should formulate DSLs. So I have been looking into systems engineering for a while. It sounds like a great career path. Yeah, that is a sort of a side note, but yeah. So a DSL for DSLs is then a very powerful thing. Now, let's say I have a companion, an all-knowing companion that I just need to say, solve a problem. And it understands that there is a problem because I'm expressing so. And let's say I give it my base abstraction is either I can indicate it a yes as in solve a problem, and a success as in the problem has been solved. So these are the only two base abstractions that I can give it, and the rest it has to figure out on its own. So it probably starts exploring. It probably understands the world around it. It sees what might the issue be. It sees how I am reacting to the actions it is taking based on its questions to me, based on its feedback loops from me via me when I say if a problem has been solved or not. So I am sort of acting as the oracle, the all-knowing person, forming the basis of if a problem has been solved or not. So this sort of very generic problem oracle, as in if a problem has been solved or not, that sort of a machine, coupled with a very exploratory solver. You give it the base abstractions, you give it access to all sorts of base abstractions, math, physics, all sorts of things. A triager, a sort of a quick triager to understand what the surroundings, sort of a context manager, a context comprehender. Give it all sorts of fancy tooling that you want to. So this is a very generic insight into a problem solver, a generic problem solver. For example, in the case of a convex optimizer, yeah, you'll probably need a way to understand if a problem has been solved. So probably a way to test convergence, or a mathematical surety or proof or assertion that this is the way to solve a problem. I mean, if you get the local optimas, you get optimas based on setting the nabla of the potential function or to zero. I mean, I'm using physics terminology, but then that's how I think. So scalar fields and stuff. Yeah. Okay. So the thing is a generic problem solver, as in to build the meta DSL, the meta domain specific language, is sort of a very noble pursuit. Now, why I think natural language is not it is very vague. There's a lot to interpretation, and by the time you end up iterating to actually solve the problem, you end up inventing your own caveats and having your own assertions based on what the solver should do, shouldn't do. So natural language in itself is it's convenient, but it's not all powerful. It's convenient when you do not want to replicate the solution again and again, which is not usually the case. You're not, if you're going for efficiency and if you're going for speed in the longer run, you probably will be seeing that problem sometime again. So a DSL to solve it is going to help you solve it the next time in a faster manner. The best way to be efficient over the scope of your life, over the span of your life, is going to be building DSLs to solve problems, and solve the problems with those DSLs and improve upon those DSLs over time, based on the number of problems you solve over the course of your life. Natural language forces you to adopt a lot of assumptions, adopt a lot of abstractions that you yourself are not completely clear with. There's no clarity out there, and you will have to understand and iterate upon those assumptions at the time of solving a problem. So if you want a quick fix, if you want a snappy duct tape on it, if you want to be a glue engineer, not a glue engineer, that's the wrong term. No, not a glue engineer. If you just want to weld joints without measuring, yeah. If you want to cut twice and never measure, use natural language. But if you want to, yeah, probably measure twice, probably imagine pseudo cuts and just cut once all your life. Try building DSLs. So even with the, okay, so now this is some modern take on it. The act of converting natural language to the corresponding DSL with assumptions and and uh, intuition could be delegated. Of course, it's delegable. I'm not sure what the word is, but yes, what you need for that is data. So LLMs today don't just they don't quite understand what the assumptions surrounding making a cup of coffee truly are. They just statistically choosing the most probable thing that I'm asking for. If I ask an LLM to make a cup of coffee for me, give me the recipe to make a cup of coffee, it is not going to tell me to probably just make some coffee first and then freeze it into a cup mold. It is probably gonna give me the recipe to make a cup of coffee as humans would understand it. That is because it is trained on datasets where humans usually make a cup of coffee by the way we mean it implicitly. So that problem of analyzing a whole bunch of data sets and delegating the implicit conversion of our abstract natural language, abstract in the sense vague natural language, into solidified base assumptions and procedures, behaviors, transformations, is what can be delegated. So that's the next step of working with things. But then my question to you is, how long do we wish to have this crutch of natural language when trying to work in engineering domains? Of course, if you're working in a pseudoscience, if you're working in the context of organisms that where stuff is very vague and it cannot be formulated pretty easily, natural language is helpful. It helps encapsulate a whole bunch of vague feelings into say different sorts of phrases. But in engineering domains, a lot of it, we have very powerful abstractions for dealing with a whole bunch of things. So there's probability, there's computing, there's calculus, or the whole optimization thing. There's mathematics. Mathematics in itself is super powerful. There's physics. Physics is an experimental beast. Yeah, I mean science in general. So all of these domains, to know the DSL of the meta DSL that will help you sort of solve a problem. Now there can be different sorts of problem, of course, but then to know the DSL that helps you solve the problem at hand is the best way to go about it, in the sense that in terms of long-term efficiency, to truly understand your problems better, just start out by learning the vocab around it, truly understand the vocab around it, and build it up on the abstractions you already know. If I was setting out on learning, let's say, knot theory, I mean, I know what a rope is, I know how to tie a basic knot, but then the abstractions around it, the vocabulary around it, it seems very interesting. So topologies and stuff, knot theory like that would be very interesting. So I would really have to get into the weeds of understanding what actually I'm trying to do. So if I just say knot theory right now, I can show you the picture of a weird knot and you'd probably get it. That's for us right now. That's just a symbolic view of seeing what knot theory can do. But let's say a sailor probably sees it in a different way. A camper, a hiker, probably someone who's camping out in nature probably sees it in a different way. And if a mathematician sees it in a different way, a practical person, let's say, sees it in a different way. So that symbolic perception of that particular knot that I show you, for us it could just be an abstract representation of knot theory. For someone it could be a very specific, highly specific sort of knot with certain use cases. So that seeing of that particular knot probably triggers off certain situations in their head, as in like, where could this and this and this be used? Those sort of computations are triggered off, and that memory is easily accessed. So for example, if I show these headphones to a baby, probably will not be able to understand anything. But then as humans, for the baby, it's just going to be, I don't know, abstract matter. Will not be able to relate it to a lot of things. But if I show it to an adult, they'll probably have memory indices triggered into music, podcasts, or whenever they sort of use any sort of headphones. So yeah, that's that. So to really solve problems, you have to be good at understanding and formulating the domain around it, rather than expressing it in natural language, trying to build a DSL for it, or expressing it in domain specific languages is the power move to actually solve the problem with efficiency and with asserting your presence in the problem and asserting your solutions in the longer term. So how do we use this? Of course, there's a whole bunch of DSLs for hard engineering domains, but then trying to build DSLs towards the pseudosciences is sort of where you could start exploring it. So I am not personally a fan of, say, diagnosing myself with conditions, ADHD, neurodivergence, that sort of stuff. I've said this in previous videos, but that is a DSL related to, say, psychoanalysis. You could probably get into Jungian stuff, Nietzsche, reading philosophy, philosophers, the boundaries of philosophy and psychology, psychoanalysis, that sort of stuff. Freud, you could probably read up on those. You could build up your vocab in natural language, but soon you start understanding what the ego is, what the psyche is. So if you really wanted to truly understand just the nature of linguistics and language better, you could get into etymology, you could get into semiotics, just study metalinguistics. So what are the things that help you solve problems in a very generic manner? I would say symbolic computation, symbolic algebra, semiotics is the way to go about it. If I wanted to solve the act of solving, as in solving, I would go with symbolic computation via Lisp to express the DSL that I'm working on. Just because of the expressiveness, the power, and everything, and just how simple the base abstractions are, and the power that it renders you with. That's another video in itself. I'll start rambling about Lisp as well on the bitmage. I think we can start doing that now. Yeah. So I think we can start. Working on simultaneous videos with the bitmage and and Conver Industries. Here are the cognitive aspects of it, and there I can have the technical aspects of it. So yeah, Lisp and trees and expressing stuff symbolic computation. Yeah, why not? But yes, today the point of today's video is don't limit yourself to natural language, is what I'm saying. Put in the effort and build your own DSLs. Try understanding the problem better. Use more defined vocabulary. Try to understand the jargon behind stuff. Because anecdotally speaking, it does wonders. Neuroscientifically speaking, it probably also does wonders, which I cannot express right now. I'm not capable of expressing those wonders right now. So I will have to get into the domain of neuroscience and understand its vocab, its jargon, its DSL to express that properly. So what actually is happening? That is actually the name of the game. If you really want to comprehend anything, express anything better, just dive into the DSL of the thing, the vocab of the thing. So language is fairly powerful. Understand that first, and then you can start expressing behaviors, attributes, and transformations surrounding that particular domain in the form of symbols and work on symbolic transformations or symbol applications on symbols. Yeah, that's just a hint at lambda calculus. Yeah, yeah, I think that's it for today. I think it's a nice stage to start going on to the Bitmage for technical stuff. My coffee runs cold every day. I probably need to make these videos limited until the coffee runs cold. It's 25 minutes. I think I'll have to time how long my coffee can survive not running cold. I'll have to iterate. I'll have to converge. I'll have to have this as a sort of a mental timer. Probably okay. This is a very good gauge into having a cup of coffee with me. That could be a good experience we all share together as an audience. Have a cup of coffee with me until it runs cold. It's probably like 200 ml. I heat it for 2.5 minutes and I set up my desk setup for like 10 minutes, 5 minutes before I actually start drinking the coffee. So it's been 25 minutes and it's pretty lukewarm right now. It's not fun. So I need to probably limit my videos to 20 minutes at most to really encourage you drinking a coffee with me. I mean, I don't want you just sitting with a cup in your hand later on. Well, yeah, this was the Bitmage, the founder of Convert Industries. We have our partner channels, on YouTube, the Bitmage. This was Convert. Yeah, I philosophically ramble out here. I think of solving stuff. I think of pragmatic applications of wisdom in here, and there I do sort of the knowledge part. So knowledge and wisdom sort of go hand in hand, is what I believe. Yeah, knowledge and wisdom go hand in hand. Here is where I try to be wise, and there is where I try to explore knowledge and be more wise about using knowledge. Here I try to be more knowledgeable about wisdom. It's all okay. This is another video. I mean, I'll do it. I know I've been thinking about this for a while, but then I'll do it. Yeah, I'm trying to be knowledgeable about wisdom here, just trying to understand the nature of wisdom out here, and there I'm trying to be wise how I apply knowledge and what I do with it. So that's that. Check out that channel as well. Check out the blogs. You got I think that's the bitmage.com, and that is convert.com. So check them out. Thanks for tuning in.